G'day and welcome to the video for exercise 6.5. Using calculus to find maximum and minimum values for application type questions. Sometimes in these questions, the easier type questions will have the actual equation. You find, looking at the equation, you get the derivative, make it equal to 0, find the x value, and then you'll either find the minimum or the maximum. You can test to see which one is a minimum or a maximum. But often, and I guess I won't show you many of those questions because I think they're fairly straightforward. The textbook has a couple of examples as well. But what I want to show you is when they don't give you the equation, when it's a little bit more tricky because you actually have to find the equation yourself, then do the derivative, make it equal to 0, and then you'll find the minimum and or maximum value. So here's an example that you don't know the equation of. A rectangular piece of canvas with dimensions 10 by 6 is used to create a children's swimming pool, or a child's swimming pool. Equal size squares are to be cut from each corner, and the remaining canvas will be folded up around metal tubing and framing, and the corner seams sewn and sealed. Find the dimensions of the pool correct to 2 decimal places so that the volume of water contained will be a maximum. Okay, so I don't know if you understand what that is talking about, but essentially we've got a piece of material here that we're going to cut corners out, and we don't know how big the corners are going to be, but once we cut the corners out, we're going to sort of fold them up and make like a kid's swimming pool to put some water in. Now, we could change this the corner dimensions, x and x, but we don't know how big we should cut the corner. We don't know whether we should make it a really big corner or a really small corner. It will affect the overall volume in this thing, in this pool. If we make it a really big if we make the x value really big, so the corners are really large, we'll end up cutting something like this. Okay, and so we'll have, I guess, a long, skinny pool, something like that. If you make the x values really small, you'll get like a fairly deep, a fairly shallow pool, but like I guess fairly wide as well. It will affect the overall maximum of it. I guess one thing we could do is find out the equation of the volume of this particular pool. The volume is going to be the height, which is x, because that's how high the pool is going to be once we chop out a corner, multiplied by the length, which is going to be 10 minus x, or minus 2x, and then the width, which is going to be 6 minus the corners, which is x and x, so 6 minus 2x. And we end up getting 60x minus 32x squared plus 4x cubed. Let me just show you this on a graph. So let me go to my calculator and let me go to a graph page, and I cannot remember what the equation was. 60x minus 32x squared minus 4x cubed, I believe. Okay. Before I show you the graph, I just want to think about what values x can have and what values x can't have. Obviously, x can't be 0, because if x is 0, you don't get a pool. You've just got a flat piece of material. But if x can't be 0, and it can't be a negative number either. But x can't be anything. It can't be a large number, because at some point there's going to be some limitations on this. For example, x can't be bigger than 3, because if x is bigger than 3, we actually, our cut will be somewhere over here. From this edge, if I measure 3 meters, it's going to be, say 4 meters, it's going to be there. And then I would need to measure from here and make it 4 meters that way as well. And the cuts would actually overlap themselves, so that's not possible. So I also know that x needs to be greater than 0, and it also needs to be less than 3. Because if it's greater than 3, there's not enough material, and if it's less than 0, then you actually don't get a pool at all. Okay, so now I can go back to my calculator, and I think I made a mistake before. I think this one should be a plus, not a minus. So I end up getting this graph just here. Okay, and now I can find out my maximum value along here. I guess I'm going to do it using calculus first, and then I'll go back and actually find out the maximum from this graph just here. Okay, so I go back and I expand it, I get the derivative, I make the derivative equal to 0, and as you can see, I get 3x squared minus 16x plus 15, But it does say to use the corrected 2 decimal places, so I guess I can use the calculator at this point. So when I go to my calculator, if I did the solve function, I'd find 2 answers. One of them's outside of my domain, but let me just prove that the other answer is correct. So I'll find the maximum here, and ask me lower bound, good, and then oh no, whoops, mean is 6. What is it? 3. So I'll find the lower bound and then the upper bound. So my x value is 1.21, the corrected 2 decimal places, and my y value is 32.884. So that means that the x value, the bit you have to cut off from the edges, is 1.21 meters to get the maximum. And then when you do cut it by 1.12 meters, you'll get a volume, and the maximum volume is 32.84 liters, I guess, in this case we're looking at. Okay, so I guess the dimensions of the pool, we need to actually answer the questions. All corrected 2 decimal places would be 1.21, and then 6 minus 2 times 1.21 is 3.58, and then the other one is 7.58 meters. Okay, so that's how we would go about doing this kind of graph, this kind of question. The next video I'll have a look at another one that comes up in lots of different exams and SACs and things. So thanks for watching.